Unit 8, Atomic Theory, Lecture 1. In this unit, we're going to cover a brief history of atomic theory. We'll talk about the electromagnetic spectrum. We'll discuss some of the aspects of the Bohr atom. And we'll talk about what we're choosing to call the modern atom. And then we'll talk about the alpha.
What is this atom? What does it look like? How do we know, and why is it important? For hundreds of years, scientists have looked for these answers. They've tried to figure out what the atom might look like. But is it really necessary? In the first place, seeing an atom is not easy. How do you see things? You bounce photons off of them. They come back to the eye and are received, or to some detector and are received. The problem is the things we might bounce off of an atom in order to see it are too large. So what we have to do is develop a model of the atom based on current research. The current research tells us the atom behaves a certain way, so we devise a model that will explain and describe and predict that behavior. And as more information and research comes in, we have to change our model to meet those new informations that we're getting. The idea is that we want to develop a model that will allow us to explain to some extent and, importantly, to predict behavior. Now, what we're going to do is we're going to look at the historical view of the atom, and we're going to look at it through the eyes of the researchers. And we're going to look at these as they try to determine how the atom is behaving when they evolve, when they see these characteristics that are evolving. Expect our models to change. So the models that we're using in this lecture may not be the models that are used several years from now. But the idea is, it gives us a way to project and predict.
In this history, we're going to talk about the early 1900s and the work of J.J. Thomson. Then we're going to go to Ernest Rutherford and the work that he did in 1910. In 1913, we will talk about Niels Bohr's work, coming very close to Ernest Rutherford's. Then in 1925, that was the work of Louis de Broglie. In 1926, right then, Ernst Schrödinger's work, and in 1927, Werner Heisenberg. All of this occurred in a narrow band of time, about 26 years, and it was a very, very important period in the whole idea of atomic theory. Let's start with J.J. Thomson and his work in the early 1900s. He gave us what we call the plum pudding model, because he envisioned the atom as a sphere of positive matter in which thousands of electrons circulated in rings. That was his initial thinking. He later modified that to be a sphere of positive matter with a much smaller number of electrons circulating in there. And the smaller number of electrons, the number was unique to each element. The number was corresponding to the element number, which has, by the way, nothing to do with atomic number. Further, he went ahead and noted the mass-to-charge ratio of the electron. In 1910, Ernest Rutherford tested Thomson's atomic theory by bombarding gold atoms with alpha particles, thin sheets of gold with alpha particles. Alpha particles are essentially the same thing as the nucleus of a helium atom, but he bombarded them with alpha particles instead of electrons. Thomson had bombarded his with electrons. Now here's an idea of how Rutherford's experiment went. He had a radioactive material that emitted alpha particles. That's over on the left. That's kind of a glob. and it was firing alpha particles at the thin sheet of gold foil. Now, the whole apparatus was surrounded by a scintillating material, such as zinc sulfide, that would change colors when the alpha particles hit it. And so he fired the alpha particles at the gold foil, and it occurred as he expected that most of them went through, but surprise, surprise, every now and then one would be deflected. As a matter of fact, sometimes they would be bounced back, literally to the source. And so he said, well, maybe Thomson is wrong. Maybe we should look at the atom more as a material with a center, a highly dense positive center that can repel that alpha particle. Rutherford concluded Thomson's plum pudding model just would not work. Why did he think this? Well, remember the repulsion that was experienced by those alpha particles? He had to conclude that atoms have a highly dense center of positive charge, the nucleus, and that electrons are not in this dense center. Then that raises the question, where and what are electrons? Enter Niels Bohr in about 1913. Now, Bohr was working on the same kind of thing that Rutherford, Thomson, Rydberg, Paschen, Pfund, and some other physicists were working on. In other words, working on light emission spectroscopy. Now, what happens is, if you energize an element, if you heat it, but you energize it so that the element is excited and it glows, then they would evaluate the light that was emitted, and they found that it was a series of lines instead of a continuous band. So let's pause what we're doing right now with history, and let's look at a little bit of light emission spectroscopy. And then we're going to talk about the others, Rydberg and that crew, when we come to their contributions. What is light emission spectroscopy? The easiest way to explain it is to show you some examples. For example, what happens when visible light passes through a prism? Think about a beam of sunlight passing through droplets of water. You get the rainbow. And here it is. This is a spectrum from visible light. This is called a continuous spectrum. You can see all of the bands of color coming one right after the other, merging into each other. Here is a spectrum for sodium. When we take sodium and heat it until it glows, and we pass that light through a detector, or I pass that light to a detector, pass it through a prism, instead of getting the whole range of colors like we do for visible light, we get some specific bands. Now look at this one for hydrogen. Here we have a number of bands. The thing that you're going to find is line emission spectra are discontinuous. They show very specific bands. The question is, what causes them? Before we get into what causes these, let's answer another question, and that is, what is an absorption spectrum? The absorption spectrum is the appearance of dark lines. I think the easiest thing to do is for me to show you. This was our continuous emission spectrum. Remember that? And remember this one, the line emission spectrum from hydrogen? Well, this is an absorption spectrum. Notice what is happening here. We have, instead of getting the continuous emission, we're getting some areas in which there are dark bands. That is where something has absorbed the light, and the light in that particular frequency or that particular little point of color cannot get through to the detector. Well, we're going to be dealing with emission spectra from sources that are emitting light. If you study line emission spectroscopy or emission spectroscopy, you may hear these names mentioned. That was Balmer, who was doing work in the visible region around 1885. This was a period of time in which there was a lot of really intense work going on. Lyman was working in the ultraviolet. Paschen, Brackett, and Pfund were working in the infrared region. And Rydberg was doing some work in 1889 as he was trying to make sense of all of this. Let's look at Johannes Rydberg's work for a moment. He was studying particularly the spectral lines of hydrogen. Now, you've seen that spectrum. But what he was doing was he was measuring the frequency of the hydrogen lines in the visible spectrum. He was looking at these individual lines and he was measuring their frequency. He deduced a general mathematical relationship describing these lines. It was called an empirical observation. He offered no theoretical explanation for it. He just simply noted the relationship that existed. And what he saw was this. The reciprocal of lambda is equal to a constant r times the quantity 1 over 4 minus 1 over n sub 2 squared, where n sub 2 is going to be a number greater than 2. And his r value is now called the Rydberg constant, and it is 1.097 times 10 to the 7th reciprocal meters. Yes, you should know that. And remember, there was no theoretical basis for this until Niels Bohr came along. Why was this happening? They didn't know. It took Niels Bohr. Other physicists noted, however, that if we took the Rydberg equation here, but we replaced the 4 with n sub 1 squared. Think about 4. 4 is 2 squared, isn't it? Yeah, okay. But if we replace the 4 with n sub 1 squared, that we could find out information about a whole additional battery of lines that you couldn't see necessarily in the visible. And it worked as long as n sub 2 was greater than n sub 1. Now remember that. N sub 2 must be greater than n sub 1. And when they looked at this, they found that if n sub 1 was 1, the wavelength they saw, the signal they got, the spectra they experienced was in the UV region. If n sub 1 is 2, the wavelength they noted, the spectra they found was in the visible region. If n sub 1 was equal to or greater than 3, then the wavelength, the spectra they noted, fell in the infrared region. Well, I think what this tells us is we need to look at the extended spectrum a little bit. When we talk about the extended spectrum, we need to know that there are such things as the radio TV waves down at the lower energy end, microwaves, infrared. There's this very narrow section right here, which is the visible region that I have expanded below it. There's ultraviolet, X-ray, and gamma ray. You will notice that as you go across, the wavelengths get shorter and shorter and shorter. The frequency then gets higher. The reason for this is the energy increases as you go across. Pay particular attention to the visible region for a minute. Red, orange, yellow, green, blue, indigo, which I have in parentheses, and violet. As you go across the visible region, that very, very narrow region, you will notice the energy increases as you go from red to violet. The wavelength then gets smaller as you go from red to violet. So if you're talking about the energy of these, you will find that the red, remember, is the lesser energy, the violet is the greatest. The red is the least, the violet is the greatest. Now, why is the indigo in parentheses? There's some debate as to whether or not indigo is actually a true color and whether or not it should then be included in the Roy G. Biv listing. So maybe our name Roy G. Biv that we've often used to remember the order of colors, maybe it has lost its vowel. Let's calculate the wavelength in nanometers when n sub 1 is 2 and n sub 2 is 4. We'll use the Rydberg equation. 1 over lambda is equal to 1.097 times 10 to the 7th reciprocal meters times a quantity, 1 over n sub 1 squared minus 1 over n sub 2 squared. All right, plugging it in. We know that n sub 1 is 2 and n sub 2 is 4, because we told you that in the problem. But if we had not told you which one was which, you would always remember that n sub 2 must be greater than n sub 1. Remember that. Okay, let's plug it in. Plug it in and work it out. Now remember, square those, take the multiplicative inverse, and then take the difference. Yeah, you remember your algebra. Well, when I calculated this, I found that lambda was 4.86 times 10 to the negative 7th meters. But I wanted it in nanometers, so convert it. Lambda is equal then to 4.86 times 10 to the negative 7th meters times 10 to the 9th nanometers per meter. Gives us 486 nanometers. Now you can look at a spectrum and see where it's going to fall. And in this case, at 486 nanometers, the line is going to appear in the green color region of the visible spectrum. Now, Rydberg could calculate this just fine. The question was, what did it mean? Another variation of the Rydberg equation was brought about by Bohr and another group of physicists. And that equation is this: energy is equal to a constant B times, oh, does this grouping look familiar? 1 over n sub 1 squared minus 1 over n sub 2 squared? Yes. And in this case, the constant is minus 2.179 times 10 to the negative 18 joules. And again, n sub 2 must be greater than n sub 1. But it allowed us to calculate energy differences. Think about it, folks. Here you are in 1913. You've been studying line emission spectroscopy. You've been studying the work of Paschen and Pfund and Rydberg and all of this crew. How would you go about explaining those lines in the emission spectra? How would you go about explaining what those n values are that they're getting? How would you go about explaining there were always discrete values there? What would you think is going on when atoms are energized and the element sample will glow and emit light, but light only of certain very specific wavelengths? What conclusions would you draw as to what's going on in the atom? And what does this have to say about what the atom is? We're ready to look at the Bohr atom. Now, Bohr showed us something interesting. He said that the energy of the hydrogen electron in the nth stationary state, now nth is a whole number, like the second, the first, the fifth, the fourth, whatever. Anyway, he said that this energy could be expressed this way, that the energy of the nth state is going to be equal to minus RHC over n squared. Now, I want you to see the equation. We're not necessarily going to work with it. He also suggested, and this is the important part, that those n states, which he called stationary states, were the only states that the single hydrogen electron could occupy. Those were the only frequencies, if you will. Those were the only energy levels that those electrons could be in. And this was the beginning of the concept of quantization, or the beginning of quantum mechanics. Why is it a quantization concept? Well, if you solve the Rydberg for wavelength, those wavelengths are discrete lines rather than a continuous spectrum. So there are very specific quantities of energy according to Bohr. What else did Bohr deduce? Based on this, Bohr developed his solar system model, sometimes called a planetary model, in 1913. He envisioned the atom as having a nucleus, a tightly packed, highly dense nucleus. with a positive charge. Remember the gold foil experiment? Sure. And he envisioned electrons in orbits about this nucleus, very much like the planets revolve around the sun. Why did he think in terms of this? Because he was able to do a calculation in which he proposed that the radius of these orbitals was equal to 52.9 picometers times n squared. And what is n? N is 1, 2, 3, 4, etc., on out theoretically to a large number, but whole numbers representing those various orbitals. When an atom was exposed to energy, the electrons, if the energy was the right amount, the electrons would absorb energy. They would absorb energy and move to a higher energy level. And when the circumstances were right, the electron would emit energy and fall to a lower level, not necessarily the same level, possibly another one. And they would emit the energy and we would see it as light. And that is what accounted, according to Bohr's theory, for those lines in the emission spectra. There are some points in Bohr's theory that we must mention. He concluded that electrons were particles. He further thought that electrons orbited the nucleus in one of a number of orbits, and that's where that n is 1, n is 2, and so forth comes from. And as the value of n increased, the atom was less stable. In other words, the electron had more energy. He added something else in there that's very important, and that is the maximum number of electrons in any particular orbit could be determined by using the formula 2n squared. That is the maximum number of electrons. It was a brilliant deduction, but there were problems. It only worked for hydrogen. It did not explain why electrons did not spiral into the nucleus. Think about it. If as the electrons move around the nucleus, they are expending energy, why don't they eventually lose sufficient energy to spiral into the nucleus itself? Further, Bohr's theory assumed that electrons maintained a defined path, in this case, an orbit, and he expected electrons to obey the laws of Newtonian physics. In other words, the laws of mechanics. Okay, so why did it fail? Well, let's look at the conclusions of Heisenberg and the research that he was doing. Maybe that will explain it. Heisenberg produced what is an uncertainty principle. And in this principle, he says, you cannot simultaneously determine both the position and momentum of a particle, because whatever you do to locate the position of the particle will cause you to change its path, or whatever you do to locate the path of the particle will change its position. So the problem then is Bohr's electron orbits are too well defined. There's no way that you could know that they're like that. Further, de Broglie asked, he was also doing research, if radiation has moving particle characteristics, shouldn't moving particles also have wave characteristics? Further, de Broglie explained, lambda, wavelength, is equal to Planck's constant over the mass times the velocity component, where lambda is the wavelength associated in this case with a moving particle. H is Planck's constant. Get this down. It is 6.626 times 10 to the negative 34 joules seconds. Planck's constant. M is the particle mass, and it must be expressed in kilograms for reasons I'll show you in a moment. V is the particle speed, or the velocity, in meters per second. Now there's something in all of this that you have to remember, and that is this. Joules is equal to kilograms meters squared per second squared. Now we're going to work two problems with two objects of entirely different size, and we're going to look at their respective wavelengths. In this problem, we're going to take a baseball that weighs 5½ ounces and that is thrown at 100 miles an hour. Yes, a good fastball pitcher can throw it at 100 miles an hour occasionally, but not as a steady diet. And we want to know what is the characteristic wavelength of this moving baseball. Can we see it? Are we going to see a color? Are we going to observe a wavelength at all here? Let's find out. To calculate this, the first thing we're going to have to do is get weight in ounces over to kilograms, for reasons which you will see in just a few minutes. So let's convert ounces to kilograms first. We start with 5.50 ounces, and we're going to convert that to kilograms. So let's see. I know that in a pound there are 16 ounces. My ounces will cancel. And I know in a pound there are 453.6 grams in a pound. So now my pounds cancel. Good. Now I've got to have it in kilograms, so I know that in a kilogram there are 10 to the third grams. So my kilograms are going to cancel. Now my grams are going to cancel. You have to listen to what I mean, not what I say sometimes. And that's going to get me to kilograms. And when I do the calculations, I come out with 0.156 kilograms. You may want to pause this and see if I'm right. Okay, now we've got that. Now we're going to need to get the speed, that's speed, in meters per second. So we're going to get the speed, which is at 100 miles an hour, converted to meters per second. So let me back this up here and get rid of some of this, so I will have room to work. Now, here we go. Just about got rid of too much. 100 miles per hour times, let's see, go to feet, 5,280 feet per mile. You know that, don't you? Yeah. You had to learn that in grammar school. Unless, of course, you're not working in the English system and you think we're a little nuts. Times 12 inches per foot. So feet cancel. All right, we've got that. Times 2.54 centimeters per inch. Inches cancel. Times, let's see, we are now at centimeters, and I've got to get to meters, so I know that in a meter there are 100 centimeters. So centimeters cancel now. So now I'm at meters. Oh, we've got to get it to meters per second. And let's see, in an hour there are 3,600 seconds. Did you know that? I bet you did. So when you stop this and run those calculations, why don't you stop it and run those calculations for a minute? And I'll cancel hours up here. When I ran it, I got 44.7 meters per second. That's an SEC. Well, why don't we just say S and be done with it for seconds? Yeah, that's much better. Now we've got to convert this. So let's see, what do we know? We've got to get wavelength out of this. What do we know? Well, lambda, which is wavelength, is equal to Planck's constant over the mass velocity factor. Well, let's see, that's going to be equal to Planck's constant, 6.0 626. Do you see that decimal right there? Yeah. Times 10 to the negative 34 joules seconds over 0.156 kilograms times 44.7 meters per second. Yeah, okay. Now look at that. Nothing cancels. Don't tell me that you think seconds cancel, because they don't. That second right there, and that's the second here, and the second here, and the second here, you know what's going to happen with them? Yeah, that's right. They're going to come out to be seconds squared. So let's get rid of that. Okay, it's going to be seconds squared. So nothing cancels. And when I work this out, it comes out to be 9.50 times 10 to the negative 35th joules seconds squared per kilogram meter. Yeah, there we go. Okay, now we got to get wavelength out of this. And there's something I want you to remember. I want you to remember that a joule is equal to a kilogram meter squared per second squared. Now write that down somewhere and remember it, because I'm going to use this. That's the same thing as saying we've got a kilogram meter squared per second squared joule. And this is the factor that I'm going to use right here. So let me clear this out of my way because I need that space. So I'll get out the magic eraser and get rid of all of this so I can finish up this problem. And what I have is, I have 9.50 times 10 to the negative 35th joules seconds squared per kilogram meter. And I'm going to multiply that by a kilogram meter squared per second squared joule. Now watch what happens. Joules will cancel. Second squared will cancel. Kilograms will cancel. And meter will cancel the square and leave me with meters. And this comes out to be, when I work it through, 9.50 times 10 to the negative 35th meters. But I don't want it in meters. I want it in nanometers. So let's take that and multiply that by 10 to the 9th nanometers per meter. And what happens? We come out with 9.50 times 10 to the negative 26th nanometers. Well, it's a lot of wiggly there, isn't there? Nanometers. Yeah. Folks, that is short. It's totally outside the visible region. You won't be able to see anything. As a matter of fact, that ball is moving so fast you probably won't even be able to see it. Keep that in mind now. We're going to use this value to compare with another problem we're getting ready to work. In this problem, we want to calculate the wavelength of a neutron traveling at 100 miles an hour, so we can compare it to the baseball. And here I've given you the relative weight of the neutron. But remember, you've got to have that in kilograms. Okay, let's start. We'll start with our 1.00866 grams per mole times 1 mole over 6.022 times 10 to the 23rd neutrons. That's right. This is going to give us grams per neutron, but we've got to have it in kilograms. So we multiply this by kilogram over 10 to the 3rd grams, so that our grams cancel now, and we come out with, or at least, I don't know what you're going to get, but I got 1 point, slide this back up where it was, 1.675 times 10 to the negative 27 kilograms for every neutron. Okay, now we've got our mass. So let's get our velocity. Well, we know this is traveling at a... Let me erase that. That's not looking real good. Let me try that again. All right. We know this is traveling at 100 miles per hour. And in the previous problem, we figured that that was 44.7 meters per second. Now, you need to work it out in here. But you can go back and look at the previous slide to see how I did it, because I need that space. So remember that 100 miles an hour is 44.7 meters per second. And I'm going to come back here, and I'm going to erase all of this. Yeah, exactly. Now I'm going to use lambda. And lambda is equal to Planck's constant over the mass velocity factor. And that is equal to 6.626 times 10 to the negative 34 joules seconds over the mass, which is 1.675 times 10 to the negative 27th kilograms times 44.7 meters per second. And when we work that out, that comes out to be, do you know what it comes out to be? Sure. Work it out. Make sure you do. Make sure I'm right. That's the thing. It comes out to be 8.85 times 10 to the negative 9th joules second squared per kilogram meter. Remember that? And how did we get rid of all that stuff? Because nothing canceled. Well, we multiplied it. What did we multiply it by? We multiplied it by kilogram meter squared over second squared joules. Now what cancels? Joules cancel, second squared cancel, kilograms cancel, and the meters cancels the square of meters. And this is going to come out to be 8.85. Let me take that last thing off there. 8.85 times 10 to the negative 9th meters, but we need it in nanometers. And you remember that there are 10 to the 9th nanometers per meter. So this gives us 8.85
nanometers. That's for the neutron. How much was it for the baseball? Well, the baseball was 9.5 times 10 to the negative 26 nanometers, as I recall. All right, let's talk about those differences now.
There's some important questions you need to ask yourself. First of all, which has the greater mass velocity component, the baseball or the neutron? Well, that's almost a no-brainer, isn't it? The baseball. All right. Which has the greater wavelength component, the baseball or the neutron? Well, it's the neutron, folks. So then, as the mass velocity component increases, based on what we just saw, what do you expect to happen to the wavelength component? Make note of that. Perhaps this little exercise has given you a better understanding of the relationship between wavelength and the mass of a moving particle. Well, we'll consider more about these kinds of things when we start with Ernst Schrödinger in the next lecture. A better way to teach and learn chemistry.